So welcome everybody, I'm Alessandro, I work for Red Hat in the OpenShift Multiarch team. What I'm going to present is a work that we are doing, starting from the experience that we have had in releasing and in building and releasing the Multiarch Tuning Operator in OpenShift and Kubernetes. I will start from how many of you are or are not familiar with Kubernetes OpenShift in this room? Okay, how many are familiar with Multiarch OpenShift? Right, well, I mean, if you are familiar with Kubernetes, it's easy to imagine what a Multiarch Kubernetes is or Multiarch on OpenShift is. It's a cluster that is capable of running multiple workers that can have different architectures. The reasons behind running such type of clusters are, running workloads that are optimized for a specific architecture or having the possibility of migrating from one architecture to another and then scaling down workers of a given architecture. And among the various key enablers of this cluster setup, there are multi-architecture container images. I'll try to be very synthetic on this. If in this presentation we can consider a container image being a read-only file system composed of layers with binaries that we can build. A container image is usually defined, usually referenced in a manifest, a JSON object that can essentially that points to each different layers. And you can imagine that building such a container image means building a file system that is single architecture and architecture specific. In order to support multi-architecture container orchestrator, one of the key enablers is having the possibility of having images that are multi-architecture, which are essentially images built for different architecture composed into a manifest list, which is another JSON object having a list of items, each one, pointing to one of the manifests and having a pair of OS and architecture so that a container runtime can pull the proper manifest and run it into the Kubernetes cluster. Now, the problem is that once you schedule a pod in Kubernetes, the scheduler doesn't know about which architectures are supported by that pod. And that you can essentially end up into two different situations. You can end up in a situation where you have only a manifest, and that manifest will be tried to be run by the CRI. And if you scheduled the pod into the wrong node, you will end up in a crash back-off. The CRI tries to run it continuously based on the restart policy of the pod, and it is just unable to do it. If you have a manifest list instead, and the manifest list has no manifest for the architecture where the pod was scheduled, then you have a different error, image pullback off. The CRI is trying to pull that image and never finds it. The solution to this is that as a user, you can set node selectors, you can set or node affinities in order to instruct Kubernetes about which architectures are supported by the pod that you are running. Again, in Kubernetes, scheduling refers to the capability of placing pods in nodes that can run it. And this is sort of controversial from my perspective, because the scheduler can still place a pod into a node of the wrong architecture unless the user has hard-coded this information, which is also a strictly coupling issue typical of software engineering, because the resource that you are based on can come from an external registry. This external registry can update the image, the provider of the image can update the image in order to support another architecture, and you still think you support only one. Someone can think, let's put this feature within the scheduler, but this feature requires network access. Network access in network scenarios that in Kubernetes can be quite complex and cannot be guaranteed always. The network latency is also a problem for the performance of the scheduler. The time to schedule of a pod will be impacted essentially by the retrieval of the information from the registries. And also, there are other problems related to the cluster autoscaling that essentially simulate what the scheduler does and will need modifications as well. What we came out with in the OpenShift or Multiarch team is the Multiarch Tuning Operator. It's essentially an operator that runs a controller that, well, does this work, inspects the image given a pod that is being created, and does the job that the user should do manually for instructing Kubernetes about which architectures are supported. Basically, the user creates a pods. There is a webhook that inspects intercept the creation of the pod and gate the pod from being scheduled. Once a pod is scheduled, is gated, that pod, the scheduler will never work on it until someone decides to remove that gate, which is the controller that we run, capable of, essentially, as I was saying, reconciling the pod, as in inspecting the images, patching the pod, adding the supported architectures, removing the gate, and allow the scheduler to place the pod in the proper node. This work is based on a feature that is relatively recent in Kubernetes, which is named scheduling readiness, and another feature also quite recent, which is mutable pod scheduling directives that allow users or controllers, integrators, to modify the pod specifications until they are not scheduled. Well, you can modify the node affinity for setting the architecture, but what about modifying the preferred node affinity and allowing a more dynamic control of where the pod should land? Users are not said to be aware of the workloads that they are running, or better, of the needs that a given workload has, and that those needs can vary over time. A good example for me is the interpod affinity. Let's imagine you have a network of pods out that are communicating with each other. If anyone of you is familiar with the clustering algorithms, you can think about optimizing your network of pods such that pods that communicate strictly with each other can stay on the same node and communicate essentially over IPC instead of switches, networks, etc., etc. So that we have started thinking of extending the work that we have done with Multiarch Tuning Operator and trying to think at ways to influence the scheduling processes that happen in Kubernetes. Today, in the Kubernetes ecosystem, there are centralized schedulers. You can run the base scheduler of Kubernetes, or you can fork the scheduler plugins, building your own scheduler. There are several schedulers available, third-party schedulers that you can deploy in your cluster. But each one of these schedulers should implement several strategies that the users can then use on a specific pod. What if I want to implement the clustering strategy to optimize the networking between pods, and then a possible strategy that optimizes the workload placement based on the architecture, for example? Well, I should modify one of the schedulers that does one of the two things and add the other functionality, meaning that this burden is delegated to the user or to the upstream, to the community responsible for one of the given schedulers. So the situation that we have is several pods that run in your cluster, each one pod that can be bound to one scheduler. The project that we are thinking that we want to land into as an OKD initiative, as an OKD community initiative, is named Outrigger, and essentially is framework operator that builds from this, the experience of the multi-arch tuning operator to provide ways for implementers to dynamically change the pod mutable scheduling directives and also instruct the autoscalers, the pod autoscalers, or other components like the scheduling for eviction of pods, or sometimes migration, even though it's a bit of a more deep topic. It's named Outrigger because everything in Kubernetes takes from the nautical metaphor somehow. The names are also finishing. We were just chatting about this some hours ago. But Outriggers in the nautical environment is a tool. I'm not from the nautical environment. I wish I could, but I'm not. So if anyone is, please correct me. Outriggers in boats are essentially elements that allow to give more stability to the boats. They are composed of floats that float in the water, struts that are the elements that provide the structure attached to the boat, and essentially once they are attached, your boat can stay more stable in challenging waters. They are different based on the type of boat that you are running. They are different, type of boat that you are navigating. And somehow they, I think they represent what Outrigger tries to do based on the challenging water that you are navigating with your container orchestrator. I don't know, HPC workloads, long-running services, multi-architecture Kubernetes clusters, network-intensive workloads. The idea is that we could compose different strategies, binding them to different parts of a single cluster and influence the scheduling process as well as the autoscaling, the scheduling and pod autoscaling. This is a work that is currently being in progress somehow, that we wish to publish soon and share with the rest of the community. This is the first presentation about it. The idea is to go essentially from that previous environment where there are centralized schedulers that can be bound to pods, to another environment where the centralized schedulers continue to exist. We don't want to replace them at all, but we can interact with them and do some work that users might not be able to do sometimes, or that users cannot just do because, as I was saying, the dynamicity of the life cycle of a cluster can change over time. And again, it's the beginning of an initiative, and if you have any questions or what we would like to understand, if eventually this can have an interest from the community, OKD community, people from the Kubernetes community, cluster administrators that I believe are in this room.